Thanks for joining. Okay. So let me move this guy over here. So yes, I will be discussing, as Nicola said, basically modeling of interfacial multiphase flows. I'll explain what that means. And I will touch upon machine learning, which may be more interesting for you, but please take this as a short lesson in diffuse interface modeling with a specific way of doing it. So this was work that I basically conducted mostly at Stanford with funding from owing, NASA, and DARPA, and under the supervision and collaboration with Ali Mani's group at CTR. And now I'm at KTH. Most of the work is from Stanford, hence the theme of the red theme from there rather than the blue theme from KTH. So this is not.
I think it's because you yeah, a little bit. We'll try again to do. Yeah.
Okay, perfect. Thanks. Okay, so just a quick introduction to what I do, what I'm interested in general. So I have a lab in KTH called the Multiphysics Flow Lab. Our research is in the intersection of basically flow physics, scientific computing, numerical methods, HPC, and machine learning. And in particular, I'm interested when these intersect, of course. So that's when you have complex multiphysics effects and multiphase flows, when we have multi-scale models, meaning when basically models that can treat the large separation of scale we have in multiphase flows, and also reduced order models, which I assume you guys are familiar with. So just as some examples, when it comes to developing high performance code and high fidelity simulations, this is the type of things we look at, both canonical cases and maybe more relevant practical simulations as well. When it comes to multi-scale models, I'll give a very brief introduction to this work we did. Basically, this is a model that takes care of unresolved breakup events for droplets and bubbles using machine learning, right? So this is one way of doing multi-scale modeling with hybrid solvers, where you still have the large scale resolved, and then the small scale is basically input from a machine learning library. And last but not least, of course, reduced order models. We do all these simulations, we try our best to do things fast here, but the reality is for any sort of digital twin optimization design problem, we need reduced order models. So this is always going to be of interest to our group as well. And I'll give a detailed presentation of this part towards the end of the talk. So we'll start with basically modeling the direct numerical simulation of multiphase flows with the diffuse interface method. And then towards the end, I'll switch to machine learning for multiphase flows. Is there any way I could get rid of this?
Okay, yeah.
Maybe I can move it. It's more and hide. There you go. All right, so let's get right into it. So starting from the diffuse interface modeling of multiphase flows. Essentially, for those of you who don't know what I'm talking about when I say multiphase flows, I'm dealing with flows where we have two different immiscible phases, right? They are separated by a capillary interface, which is sharp, right? And these are all around us. So we have, of course, environmental applications like braking waves. You have industrial, whenever you have liquid fuel in propulsion, you have multiphase flows, bubbly flows in reactors, pathogen emission when you look at COVID patients, and so on and so forth, right? So these are some examples here shown. And the idea is that we often want to be able to actually do a direct numerical simulation of this. We want to capture the physics as accurately as possible, and for that we need to do interface resolved simulations, meaning we want to capture how the interface evolves with the flow. And inherent to interface resolved simulations, there are some challenges. So first of all, we see that we have to deal with a discontinuity at the interface. This is in terms of material properties like density. You have a density ratio of 1,000 across a water-air interface, for instance, right? This is something you don't really deal with when you're doing single-phase flows. You have pressure jumps and so on and so forth. We have separation of scales. If you look at these flows, you can see that the smallest scales of physics that happens is way separated from the large scale, right? And we have complex evolving topologies. We have breakup, coalescence of features. So these are also, these must be handled in a numerical solver. And of course, we want to do these things. We want to tackle these challenges while also preserving things like conservation of mass, momentum, kinetic energy. We want to have consistency. This means both in terms of mass momentum consistency, which I'll explain, thermodynamic consistency, the laws of thermodynamics, and also reduction consistency, which I'll explain as well. And lastly, one of the challenges with multiphase flows is often that simulations break when you go to high density ratios, realistic density ratios, turbulence, and long time intervals. So, and of course, we want to do all of this with a cost-efficient and parallel scalable solver, right? So the method that basically kind of addresses most of these challenges is the one that we will be looking at. Not to say that there aren't other methods that can do this. Broadly speaking, the most popular methods that you see for two-phase flow solvers are written here. The most popular overall are basically the volume of fluid and its different variants, so geometric volume of fluid and algebraic volume of fluid. But also nowadays, even more than level set, we have interest in phase field and diffuse interface solvers. And maybe you've also noticed lattice Boltzmann is kind of making a comeback to probably mostly because of the GPU acceleration we can gain and its suitability for that. But today I will essentially focus on the method that I've personally explored, which is diffuse interface method and a specific phase field method. So this is a general idea. A physical interface is order nanometers thick. A sharp interface basically tackles this jump across one cell. A diffuse interface would tackle it across a few cells, right? So the traditional phase field methods, if you talk to someone and you say phase field, they will think about these two equations. It's either the Allen-Cahn equation or the Cahn-Hilliard equation. And you can see straight away that we are basically dealing with an equation that's trying to capture a field phi that represents the identity of that point, right? So phi equal to 1, for instance, could be your liquid, phi equal to 0 would be your gas. And when you look at the Allen-Cahn equation, you can immediately see that basically I haven't defined what W prime is, but it's a nonlinear function of phi. This is it's not a conservative right hand side. So Allen-Cahn on itself is not a suitable phase field model, right? And Cahn-Hilliard is most typically what people use for two-phase flow simulations. Now, of course, the pros of both of these are that they are simple and easy to program compared to volume of fluid methods. The cost and scalability is pretty good. They're just basically advection, diffusion, reaction equations. Cahn-Hilliard has a fourth order derivative, but you can see how you can implement this in a numerical solver, right? It's not outrageous, right? And of course, the nice thing is that you have smooth fields, which gives you a lot of regularity in doing your operations. So as I said, the Allen-Cahn is non-conservative. It's good for problems where you have phase change. Cahn-Hilliard is basically the most popular phase field method. It has fourth order derivatives, which makes it a little difficult to deal with. It has some unwanted issues even on the PDE level. So you have coarsening effects, meaning that your droplets and bubbles might just spontaneously shrink, which is not great. And you don't have boundedness of your fields. So your fields would exceed what they're supposed to be. You would get 1.02 or something for your phi. And of course, this will translate to density values that could, for instance, become negative, right? So this motivates the development of a new phase field model, which is the so-called conservative Allen-Cahn model, also known as a conservative diffuse interface model, CDI, various things. And so the first persons who introduced this were Chu and Lin in 2011. So you can see basically this model is essentially, it's a second order PDE like Allen-Cahn. That's why it's an Allen-Cahn based model. And the derivation, however, it's not really, it's not super clean in how you go from Allen-Cahn to this. And as a result, you lose some of the properties, which I'll explain in a bit. But essentially the idea is that in the right-hand side of this equation, you have a diffusive flux and a sharpening flux. And the balance of these two gives you a nice, smooth interface that's well-defined and has a finite interface thickness. Now, the issue was that the implementation of Chu and Lin basically had some difficulties. It was a very specific type of discretization and this specific type of mesh. And they basically had to do mass redistribution to get rid of their problem with boundedness of the phase field. So we started basically working with this model now maybe 14 years ago or something like that. And the model that we created was a model that has such nice properties. It's on a standard staggered grid, second order central differences. You are guaranteed to have bounded solutions. You have discrete conservation of mass, momentum, and kinetic energy, this is basically a secondary conservation you get. And it's consistent and conservative, meaning that you can do high Reynolds numbers and high density ratios. And we claim that it's easy to implement. And of course, because it's just an equation that you solve, it doesn't really harm you in terms of load balance and cost. And as I will show, it is a modular way of dealing with multi-phase flows, meaning that you can add effects like, say, heat and mass transfer by just modifying the PDE, right? And I'll show that today. So the downside is two things. Let's say if we compare to, say, volume of fluid, the main issue is that basically you have errors that correlate with interface fluids, right? And as a result, if you want to do the same simulation of volume of fluid versus diffuse interface, often you need a factor of 2 more resolution of diffuse interface. With the way basically we are doing HPC nowadays, that it is promising, given the scalability promises of diffuse interface compared to volume of fluid, but still that is a reason why a lot of people are still hesitant to switch from volume of fluid to diffuse interface. And then compared to the traditional phase field methods, there is this issue of not having a free energy. So a lot of the thermodynamic properties that the previous slides models have, this doesn't really have, right? So we have to derive equations in a different manner than just energy constants. Okay, so that was a general introduction of the equation I'll be working with. And so let's go through this, starting from robustness. So the general equation, you can actually analyze it quite easily in 1D with an explicit Euler time stepping. And it turns out that if you can achieve boundedness and stability in this limit, you will be fine for higher order explicit numerical methods and also multi-dimensions with just a factor added. So essentially we have advection, diffusion, and sharpening, and of course you can discretize this. And the question we basically answered is a simple question. If a solution is bounded at time step k, will it remain bounded for time step k plus 1? If you think about it, if I didn't have this diffusion, in particular the diffusion, but also the sharpening, you are basically doing pure advection with second order finite differences or finite volume, and you're going to have crazy overshoots and undershoots, you're going to blow up, right? So the question is, what do we need in terms of these parameters, this gamma and this epsilon, to ameliorate this issue, right? And it turns out that there's basically this nice theoretical proof, and there's this boundedness plot that says basically if you're above this line, you have enough diffusion to overcome your overshoots and undershoots, your dispersion errors. And so essentially a lot of times when I do simulations, I either choose this point over here, so epsilon over delta x of 1 and gamma over u of 1, or somewhere like down here, right? And so basically the main message here is that you get boundedness for free. You don't need to basically take this mass that you lost somewhere and redistribute it to regain conservation. And the main issue, the main benefit of this is that when you couple this to Navier-Stokes, phi and rho are linearly related. So essentially, if for instance you have even say like 1% negative phi values, that will turn into a negative density when you're dealing with air and water, right? So this whole problem and how you deal with it is completely avoided with this nice property. So momentum transport. Essentially, this is the equation. We talked about the 2 free parameters here, how we deal with them. So they're basically numerically derived. There's no physical argument so far for these guys. And so, as I said, rho is related to phi in a linear manner. And from this, basically plugging this equation into here, you can see that you are basically redistributing your mass, right? So you have a conservative flux of mass that's basically going from one way. So you have a change in your continuity equation. And this is, of course, given here, but the main idea of this paper was that we essentially argued that you need to account for this conservative yet artificial mass flux. And the way you do it is actually pretty simple. You just account for the momentum it contains, right? So it's just a term that's added to the advective term in the Navier-Stokes. And with that, you can basically show that in the absence of surface tension forces, I don't think I'll present surface tension forces today, but this is just an explicit term. And in the absence of basically viscous forces, you will get kinetic energy conservation. So mass and momentum are conserved, and then kinetic energy is only dissipated by viscous forces, which is quite nice. And then, so for uniform staggered Cartesian meshes, and even for non-uniform, for basically stretched meshes, you can define a kinetic energy that basically is conserved in a discrete manner. And so one of the points here is also that this PDE level correction, you can apply it to any phase field method that you can write in this form, right? So Cahn as well, they have to do this. So nowadays, this is a well-known fact, but when we were writing this paper, it wasn't really an established point. So this is the overall equations. You solve continuity. So this is a one fluid system of equations. You have continuity, so you have an incompressible fluid system. This is how you track interfaces. And then basically your density and viscosity and your surface tension are all functions of P, right? And all of these go into your Navier-Stokes. And of course, your Navier-Stokes gives you your velocity that goes to the phase field equation. So it's a two-way coupled system. So, yeah, maybe I'll quickly go through this. So I just want to show basically what is the benefit of this PDE level correction. So you may think that this equation over here would work just fine, right? But it's essentially this has it violates Galilean invariance, right? So to prove this, I'm going to show you a case where we have density ratio of 10, and we have advection with unit velocity in the z direction, and we have periodic boundary conditions, a very simple case. So t equal to 0, you just have a droplet, and at t equal to 1, basically with this consistent model, with the inclusion of S, we get a solution as we want. So the drop goes back to where it belongs. And without this, with this equation, you get basically a blob that's incorrect. So this is just testing Galilean invariance, and you can see that this would fail, right? But yet you will still nowadays see people using this for this type of thing. And so another model that is quite often used is this form. So you basically take the row to the right-hand side, and this would essentially give you Galilean invariance. So this is not a problem in that sense, but it doesn't conserve momentum or kinetic energy. And it has an inconsistent momentum transport because we're not accounting for that S anywhere here. So as I said, this works well for the previous slide, but here it wouldn't. So here we have another test where we have a dense drop. So we have a very dense drop. It's given an initial velocity of 1, and the background is stationary. So you can see at high density ratios, say like 10 to the power of 4 or up or higher than that, basically it's like dealing with a solid that's being advected in a domain, right? So that the solid should not move, and that's what we see with the consistent model. So on the left-hand side, you see some variations, but it's overall much better than the next best option, which basically blows up. And we increased it to density ratio of 10 to the power of 6. We see this similar trend, and 10 to the power of 7. So these are really unrealistic density ratios at this point. It's kind of like just testing the robustness. And when you look at the kinetic energy, we see that basically the dashed line, which is the kinetic energy from this model, is a flat line. Everything else is going crazy. So a realistic case for this, we had a jet in cross flow. So this is density ratio of 100. And we are comparing the non-conservative model, the model on the right side in the previous slide, versus the conservative model. And it works, it's robust, but it's giving wrong answers, right? Wrong physics. So a simulation that works is not necessarily a correct simulation. And I mean, when you go to find a finer mesh, basically we see that this one actually blows up, which is always a telltale sign. When your finer case blows up, you know there's something going on with your PDE probably. And so then for density ratio of 1,000 corresponding to water and air, we see that it works well and it matches pretty well with what is seen in experiments, right? So that was basically how we do mass transport, how we do momentum transport. And now let's look at some applications to some realistic two-phase flows. It's very hot in here. But so this is a case that I had to do for my PhD. A few years ago, we were looking at basically microbubble generation in oceanic environments. And the cause for microbubble generation is basically the shedding of microbubbles from a retracting gas film. So here we have the initial conditions for a gas film that's basically retracting in the background liquid phase. Liquid is water here, and this is 2 microns thick, right? And so I did these in my code. It's a 3D MPI parallelized code written in C++. So we needed, I think, around 400 million. Yeah. So this is a laminar case, and despite that, we needed a few 100 million mesh points to be able to resolve the dynamics here. Yeah, we have the mesh size here. It's 200 million. And so basically, I took a 2D retracting gas film, I extruded it, added some perturbations, and then you can see the dynamics. Here we had an inflow and outflow to simulate the retracting film. And so what we saw was basically the shedding of small bubbles, which is kind of what we see in the experiments. So I'm of course not giving you a full story, but this is the reason we have thousands of microbubbles per single impact of a drop on a pool. I'd be happy to discuss this with you if you're interested, but it was a very curious and difficult problem that we had to solve with analysis and high fidelity. So just some quick examples. So I had a work where we compared this model against volume of fluid. I think it will take you too long to figure out what's happening here. But the overall message was that, as I said, diffuse interface gives similar levels of accuracy as volume of fluid with about twice the number of mesh points, right? However, when you look at the cost accuracy trade-off, diffuse interface actually, in a lot of cases, outperforms volume of fluid, right? And when you look at the load balancing, essentially, because the diffuse interface doesn't care, the cost is the same everywhere. Basically, you have no issues in scaling this. Whereas volume of fluid, basically, all the cost is concentrated at the interface. So a lot of the famous two-phase flow solvers like Basilisk and Jerris and those basically run into issues when you go to very big calculations. So some cases that we just ran, this is a gallium structure that we were looking at for an electronic device, basically how it changes shape when it changes phase. These are simulations of drops in HIT. We did thousands of simulations of drop in HIT, and we're looking at the data set together with Nicola now. And this is a very recent result from my PhD student where we're developing this model in NECO, which is a GPU version of NEC 5000. We're making some progress, but I think there's still a lot of work to be done. And this is, of course, a triplet channel with droplets. Okay, so let's go to the first multiphysics aspect that I wanted to present, heat and mass transport in two-phase flows. This is just a representative multiphysics application. And so you may know that heat and mass transport in multiphase flows is very important because in industrial settings, that's essentially how a lot of heat exchangers work, or a lot of bubble column reactors work, in nuclear reactors, for instance, or in bioreactors. Of course, in atomization and sprays, heat and mass transport plays a role. Electrochemical systems like fuel cells, clearly. And in nature, atmosphere-ocean exchanges are very important, and basically these are interfacial transfer of heat and mass between the environment and the ocean. And actually, it turns out that about 20% of all CO2 that we generate are absorbed into the ocean through events where you have breaking waves and bubbles and these types of events. So it's very important to understand this. Now, the goal of this work was to derive a model for interfacial transfer of heat and mass, so a scalar in general, a passive scalar, with arbitrary diffusivities in a system of two phases with diffuse interface models, right? Now, you may think, okay, what's the big deal? I'll explain why this is a challenge in this slide. So we have the governing equations for heat and mass, right? When we have a two-phase system in reality where we have sharp interfaces separating the two bulks, right? So we know that, for instance, for a species, a dilute species, you have an advection diffusion reaction in each bulk, right? I being the two phases. And for heat, if you write it in terms of heat content, you have an advection diffusion reaction equation as well, right? This would be inside each bulk, phase one, phase two. And then you relate the two phases through boundary conditions. So you have a boundary condition that basically enforces thermodynamic equilibrium. So this is essentially chemical equilibrium, and this is essentially saying temperature is the same, which is thermodynamic. It's thermal equilibrium, right? And then you have a second boundary condition from the second order space PDE, which essentially says that the normal flux from phase one to the interface has to be equal to the normal flux in phase two, right? And so when you look carefully at these two columns, you can see that heat and masses are essentially the same problem. They are equivalent. So we'll just deal with a scalar, a passive scalar, and represents the two. And so the general issue here is that you can see when you have a sharp interface, these are all well defined. If you have the numerical tools to do it, you can do it, right? Solve the bulk, do the boundary conditions, the gel, right? But when you're dealing with a phase field method, you don't really have an interface, right? You have a transition what is your interface? Is it 0.5? Not really, right? And you don't really have a bulk either. Everything's a bulk, everything's an interface, right? So how do we apply these boundary conditions? How do we apply the bulk equations? And so the idea here in this paper was, it's kind of a bizarre idea. We essentially assume that the interface that is diffused is basically built of an interfacial microstructure, right? So when you zoom in, basically you have a sharp interface microstructure, and applying those equations, the sharp interface equations, to a microstructure, we can homogenize to derive the diffuse interface relationships, right? So it's an interesting idea to derive upscaled transfer terms. And so here's what I was talking about. So you have a diffuse interface. This is a 1D diffuse interface separating phase one and phase two. If you zoom in, we are basically saying that there are fingers of phase two going into phase one and vice versa, and these are sharp, right? And then we assume that basically these are thin structures, right? So we assume these are long and thin structures such that we can assume that we have basically some properties like lubrication theory inside, right? Oops. And of course, to be able to be compatible with the diffuse interface, which has a tangent hyperbolic profile, we assume these also have that same profile, right? Okay, so essentially what I said is that we want to derive those equations. You might think, okay, what if I just had this equation here, C being the scalar concentration, and I have a diffusivity that is just a mixture between the diffusivities in the two phases. What happens is that when you go to large and realistic diffusivity ratios, you have leakage, right? So basically you're trying to do air-water transfer of CO2 gas, right? And the diffusivity ratio there is 10 to the power of 5 times 5, something like that. And so you get basically leakage from the water into the air, which is completely destroys your accuracy. And so for these, we need to do two scalar models, right? And so what is a two scalar model? The two scalar model basically tracks a C1 and C2, which are concentration per total volume in phase 1 and phase 2. And so you couple those to the phase field equation written here. And the equation that you have for them is of the following form. So you have this guy, which I talked about. I'm just not writing it out anymore. And then you have three terms on the right-hand side here. So this is just advection, temporal derivative. This is the diffusive flux. So the diffusive flux has to be computed using the phasic concentration, weighted by the amount of that phase and the diffusivity in that phase. So if you look carefully at this, you can understand what's happening maybe. This is a consistency correction that enforces Galilean invariance. And then we derived through this exercise that I explained from a microstructure what the transfer term would be from phase 1 to phase 2, right? And the transfer term looks not easy. So if we hadn't done that, we could have not really derived this by just making simple assumptions, right? So the nice thing is that we derived it based on those assumptions, but the model works, right? It's consistent. And all of these nice properties. So then there's also a one-scalar model that you can use when your diffusivity ratios are small, when you don't want to deal with a highly maybe turbulent system where you can assume you have thermodynamic equilibrium. But even then, you have to make sure that you have a consistency correction accounting for the right-hand side. So for instance, here, the right-hand side is moving volume from one phase to the other, right? If you think about that in terms of heat, for the same temperature, it's moving fluid that say is a liquid like water with a temperature and gas with another temperature. This movement is essentially moving heat, right? So you have a flux that is proportional to your heat capacities, right? The difference in the heat capacities multiplied by that R would tell you what you're missing, and that has to be accounted for. And the same would hold for heat, for scalar transport in general. So some examples, basically gas diffusion. I think this is a CO2 diffusion from a rising bubble. This is this is O2 diffusion from a rising bubble. This is CO2 diffusion in water from surrounding air for a simple toy problem, 2D breaking with. Okay, and phase flows. Let me see how much time I have. Yeah, I'll go through this very quickly. So essentially, we showed two phase flows, but a lot of problems are more than two phases, right? For instance, if you think about oil spills, you're dealing with gas, you're dealing with water, you're dealing with oil, right? A lot of oil systems in general have that in the petrochemical industrial problems. You have fuel cells, of course, you have three phases often, and in microfluidics and additive manufacturing as well. And so we need a model for that. And the extension was it was an interesting process. So you go from this equation written here, which I show as del dot of R, and the extension basically takes advantage of this concept of pairwise quantities. So here I defined a pairwise volume fraction for between any two phases and a pairwise normal vector. And essentially, I just extended this form over here to this form over here. And the rest is basically the same. So the momentum consistency correction is the same. The surface tension is basically the same. But through that, we gained a lot of properties. For instance, the one I may want to highlight are volume conservation, meaning that if I sum these equations up for the different phases, you get 0 equal to 0. Right, very nicely. And then the reduction consistency means that if you don't, if from your n phases m are missing, you basically get on the continuous level the n minus m phase equations directly, right? So essentially what I'm kind of harping on here is it's very important to have your equations correctly on the PDE level if you can, right? And I'm going to skip this example. And also this one. So these are some applications of basically, it's called gas flotation, where we're trying to capture this oil droplet with an air bubble, but it doesn't work. I'm going to not go into it. And some other extensions real quick. So these are work done by PhD students at in our group at Stanford. So there was a recent extension to curvilinear grids where we project the right-hand side terms to a uniform grid, and then we project them back. So you can see the Rayleigh-Taylor case that I showed a few slides ago. You can do it on bizarre grids like this, and it works fine. We have compressible flows, extension to compressible flows, as in 2 papers recently published. So here we are looking at basically a liquid. This is a PSAP project where we had the liquid oxygen jet, and we have gaseous methane on the sides. So we're looking at the gaseous mole fraction of oxygen here. Yeah. So this was for a rocket ignition problem. And then in the bottom, basically, we're looking at contact lines when your interface actually cuts the wall. That's a very tough problem that I don't think we've really solved yet. Okay, quick summary of the first part of the talk. So the conservative diffuse interface model is a viable way of doing two-phase flow simulations. It combines well with various spatiotemporal schemes. I think you have an implementation of CDI in your solver too. So I think it's a good option overall so far. And one of the nice things is that it converts surfaces to volumes, which helps in things that are confined to the surfaces, for instance, surfactants that only live on surfaces. And I talked about consistency quite a bit and some extensions. So some current activities that I'd be happy to discuss with any of you are development of basically the modern versions of my code. So we are working on a GPU-based solver called Rostang, and another one is an extension in Neko. So my student is working on both of these right now. And we're looking at LES modeling together with Nicola, and I've derived a model for surfactants, which hopefully I get to write some papers soon and submit. But this is a universal model for surfactants that would work in any limits for any conservative phase field model. All right, so quickly, I want to give an overview of some work that we did recently on autoencoders for dimensionality reduction and multiphase flows. So as you guys all know, reducible models are essential for real-time prediction, optimization, and control. And when you deal with interfacial multiphase flows where you have fields that are like this, you're going to have issues, right? And the issues I will discuss, of course, but what we looked at here was that if we wanted to do a low-dimensional representation of interfacial flows with convolutional autoencoders, nothing too fancy, just a convolutional autoencoder that has been proven to work well. What is the role of interface representation? So there's different options here, and I'll explain that. And what is the role of the shape complexity or the interface geometry here? And so through this, we've developed an autoencoder architecture that can reduce the dimensionality of such flows, and this is a building block for basically dynamics and predictions for in time. And we think that the findings for this types of work, because we're dealing mostly with shapes only, are also relevant to other problems where you are dealing with complex 3D geometries. So the idea for this work basically came from a colleague who, when they saw we were trying to develop reduced order models for multiphase flows, they said, oh, how about you are dealing with a phase field method, so you have a diffuse interface. They said, oh, how about if you basically look at the sign distance function for that and use the sign distance function as your representation and then feed that to whatever neural network you're working with. So basically, we here systematize that question. So we essentially look at the same geometry. So this is the same geometry here, but we're looking at 3 different ways of representing the same geometry. On the left, we have a sign distance function. You see that as you go far away from this interface, you basically increase your sign distance, right? That's one representation. We have another representation here, which is a diffuse interface, which is basically going from 0 to 1 in a smooth manner, in a tangent hyperbolic manner. And this epsilon is your interface thickness, a parameter that you can control. And then this is essentially your volume of fluid type representation. It's either 0 or 1, right? So for the same geometry, the question is, how would these work? So the problem is like this. So you have... Okay. Yeah, it doesn't like autoencoders.
Yeah, it's funny. You have them in these first 45 minutes.
Yeah. Too many neural networks. But so the input and the output are here, and we have an encoder and a decoder, of course, and you have a small latent space. And the question is that if we give S or phi or H to the same architecture and train the models for those specific inputs, basically which interface representation is optimal for this, and how does this change with interface complexity, right? A very controlled, small experiment. And so the data set that we used is built of synthetic data, right? Where mu equal to 1 corresponds to the most complex data set. And then the HIT data that I showed you a few slides ago, right? And so it's a fully convolutional autoencoder based on ResNet blocks. And here we have a compression ratio of 1024, I think, typically. And everything is relatively standard. The point was not to optimize the architecture. We did hyperparameter tuning, but that wasn't really the point here. And to evaluate this, what we looked at is basically metrics that look at how accurately we've actually represented or reconstructed the geometry. So that's where we went to computer vision metrics like dice coefficient and Hausdorff distance, right? So dice coefficient basically measures the intersection between two geometries. Hausdorff distance is the maximum distance between the geometries, right? In addition to relative volume error, drop size distribution, and good old visual inspection. So this is a lot. The overall message here is that for the HIT data, it seemed that all of them worked pretty well, right? So for a lot of practical purposes, basically the dice coefficient is pretty high for most of them. Even the sign distance function is pretty high. But when we went to essentially the synthetic data set, which isn't really non-representative of what you can have in a realistic problem, we saw some interesting trends. So the mu equal to 1, which is the most complex, let's just look at this first row. What we saw was that converse to what was expected initially when we started this, the sign distance function does terribly, right? So the sign distance function does terribly compared to the other ones. And then we see that in terms of the dice coefficient, basically the diffuse interface representations, the thinnest ones, and then the sharp are quite competitive. When we go to the Hausdorff distance, where small is good, we see that basically the diffuse interfaces with moderate thickness are seeming to be the best options, right? And when we look at the volume error, again, we see the same trend. So relatively thick interfaces seem to be the most promising. So we looked at this a little bit more carefully here. So here I'm looking at the same ground truth. One is tangent hyperbolic with a thicker interface. This is essentially a sharp interface, relatively speaking. So you can see that the prediction from the sharp interface is missing a lot of the small features, a lot of the small drops. Even though the dice coefficient is higher than the top one, you see that basically you are missing a lot of the nice detailed geometrical features that are captured in the diffuse representation. And we see the same thing when we look at the PDF of the droplets. We see that overall this more diffuse representation is capturing the most complex data set shown in purple. But this is the only one that's capturing this. The other representations fail. So overall, it seems that a slightly diffuse interface representation is giving us the best. And the explanation is basically based on spectral bias. So spectral bias is referring to this behavior of neural networks where the neural network fails to capture a lot of the high wave number features, right? And so when you think about a sharp interface is essentially a step function. And even if you look at the ground truth spectral content of a sharp interface, you can see that it's quite flat in comparison to this curve over here. So if you look at the numbers over here, you can see that there's a lot of energy content at the high wave numbers in comparison to the high wave numbers for the diffuse interface representation. So first of all, we see that basically the sharp interface basically has more high wave number content to begin with, which makes the neural network struggle. But additionally, what we see is quite interesting. So that was in terms of a ground truth of a sharp interface. The ground truth of a diffuse interface, we see that basically because of a regularization of the diffuse interface, there's far less energy content smaller than the interface thickness, right? Everything smaller than the interface thickness is kind of regularized. Now, the interesting thing that happens is that the model actually gains from this regularization in a non-trivial manner. So what happens is that not only does it have to represent less high energy in the high wave numbers, but it also has the capacity to learn the moderate wave numbers quite well as well. So if you look at the orange line compared to the blue, they match really well up until here, right, to the highest wave numbers. Whereas when you look at a sharp interface, essentially you have this mismatch starting from relatively small wave numbers. So essentially the geometrical features that were missing in the sharp representations reconstruction are in this range, and they are missed because of spectral bias. The model is trying so hard to capture the highest wave numbers that it even misses the moderate wave numbers. So this kind of regularization can help you basically bypass that in terms of neural networks expressibility. Okay, I think, okay, quick summary. So we evaluated the autoencoders, as I said. We see that sign distance function converse to what we expected at the beginning performed the worst, actually. And there's essentially this trade-off where you get the larger features better with a sharp representation, but you lose the smaller features. So overall, it seems like it slightly diffuses is the best option. And we saw that the spectral bias is basically the main reason for this. So we published this work recently in this new journal, AI Thermal Fluids, and current activities are to basically take this to the next level, of course. So we just reduced the dimensionality. Now in the latent space, we want to either do dynamics, basically predict trajectories, or we want to do one-shot predictions, which is useful for other applications. And then in terms of spectral bias, this is something I'm interested in, and it seems like it's quite popular in the community right now. We have explored basically adding terms to the loss function that take into account the spectral content. So there was this recent paper in JCP. It's called bin spectral BSP, bin spectral something. You add some terms that makes sure that the spectral content is at least captured in your reconstruction. But there are some issues there as well. All right, last but not least, the subject scale model for drop breakup. This is basically my last point. Okay, almost done. So the idea here was that in a lot of problems, you cannot have enough resolution. Even if you're capturing the Kolmogorov scale, you cannot have enough resolution to capture the breakup of the droplets. And so the idea here was to train a model that can predict the statistics of a drop after its breakup. So we trained a neural network that would predict the droplet statistics in a future time, and that output would be fed back into the simulation in terms of Lagrangian particles. So this is very, it's summarizing the ideas here, but we basically identified what are the quantities of interest, what statistics to use, what would be the model of a loss function, and how to input physics. And overall, it's a promising way of doing subgrid scale modeling using machine learning. This is a very, I would say, simple way of doing it. Doesn't have any sort of a posteriori training. It's all a priori, right? So with that being said, I presented essentially some work on doing high fidelity simulations using diffuse interface methods, some work on multi-scale modeling using machine learning in the context of a larger solver, and then some work on reduced total models. Thank you for your attention.
Okay, thank you very much. I mean, plenty of things still going on. So if anybody have any questions, so we can start the discussion. Yeah.
So maybe let's start. So thanks a lot. Very, very interesting talk. Can you go to slide 10, probably?
10.
It was the one on the actual numerical model, the numerical discretization.
Yeah.
So because you had like this kind of bound on for the visibility on the choice for the choice for the was this one. Okay, exactly.
Yeah,
So
this
is this exactly? So is this something like the CFL condition in the end that you have
it's
on your because like you have like the gamma is fixed, but now you have epsilon, so it's you have to
yeah,
essentially choose epsilon. So it's something like similar to that.
it's similar. It's more like a cell-Peclet condition for
Okay.
scalars,
Okay.
right? You have to have enough resolution to capture them. Here, you have to have enough diffusion to be able to capture it. So it's kind of similar. The nice thing about it is that it doesn't enforce an additional constraint on time step.
Okay, sure.
So the time step
So it's already done, it's there, yeah.
Yeah. So all we did is basically we wrote phi k plus 1 as a function of phi k, and all the coefficients that multiply phi k have to have some property, right?
And the reason to get essentially the point where you have to realize the equality is because then you have like the optimality is exactly at the
Yeah. And it turns out very interesting. I skipped that slide, but the highest time step values that you get are on this ridge in terms of CFL conditions, because the sharpening term also enforces a time step restriction. So there's a time step restriction due to diffusion. There's one due to sharpening. When they are equal, you get this line.
Okay.
So you get the maximum time step there as well. So, yeah.
Thanks.
Yeah.
Yeah.
Well, thank you for the talk. And following Federico's question, you said that you set gamma equal to U.
Umax. Yeah.
Umax. Okay.
I can explain. Yeah. Yeah. Good question. Yeah.
Yeah. I mean, what happened? I was wondering what happened where U is 0.
Yeah.
And you have an interface.
Yeah. So we were discussing this yesterday. So gamma basically, it's a universal constant, right? So it's a time dependent, but spatially constant that basically is I use L2 norm. No, sorry, I use L1 norm, right? But you can show that it's actually L infinity norm formally. So the maximum of U, V, W throughout your whole domain, that's what we would use here. I have a master's student who's working on basically localizing this, right? Because you have errors due to this right-hand side. So if you can just apply it where it's needed, that would be ideal. But so far, no, nothing promising.
Yeah, Nicola. I think the audio should be.
I am the correct Nicola.
Yeah, you are.
I know because there are several Nicolas in the group. So, okay. So can I do a question or?
Of course, go ahead.
No, okay. Thank you very much for your talk. That's quite impressive. A lot of things, a lot of curiosity, but I will restrict just to two curiosities. Can you go to the slide 12, please?
Yeah.
Okay. No, actually, it was the slide. Sorry for that. But they changed. No, the slides where you introduced the artificial term for the mass when you described the numerical method.
So it would be here, I think.
Yes, okay, it's the same. So can you provide, okay, the first thing is, can you provide details about the pressure velocity coupling in your solver?
Yeah.
And then also comment a bit how do you have selected this source term S? Because I think, okay, in the central, when you adopt the central differences, the operators need to be, are skew-symmetric. And I think that if you would like to achieve the conservativeness for kinetic energy, for the mass momentum, and so on, the only way to do that is to have that your operators are skew-symmetric. So you can adopt only central difference schemes, right? Okay. And in my knowledge, when you apply central difference schemes, your time step is really limited, right? And also you have many problems in general in the solver.
So let me go one by one. So the pressure, so this is a staggered grid, right?
Okay.
It's a staggered grid configuration, and the kinetic energy is conserved even though we have a conservative implementation for the advective term. So even without the skew symmetric, you can show that the kinetic energy is conserved, right?
Yeah.
So that's actually basically the idea is beyond that. The idea here is that you, even on the PDE level, you are not conserving kinetic energy when you don't account for this term, right? So you do gain by doing a skew symmetric formulation of advective term, but you don't really need it for at least the staggered configuration that we're dealing with here and incompressible flows. So so that's one thing. The other thing is I agree with you in terms of CFL conditions. So the CFL in 1D is 0.5, in 2D it's 0.25, and in 3D it's whatever 0.33 or something, right? So essentially with every dimension you get a penalty, and it is not great. That is essentially why I'm very interested in implicit treatment of this phase field model, but we haven't succeeded so far because of a nonlinearity. So we are looking at basically semi-implicit schemes, but I don't have something concrete right now.
Okay, so you are using an explicit scheme in your
Yeah,
system.
so typically RK4 or a version of RK3. Yeah.
Oh, wow, wow. Indeed, I thought that it was explicit because doing something semi-implicit with a sort of Laplacian of yes, a sort of Laplace equation for the pressure could be a little bit too much, I think,
Yeah.
because there is S, so
Yeah, but it's interesting. So in the Neko solver, we have actually done semi-implicit already. So for that case, basically the diffusive term is a Laplacian. So we take that to the left-hand side and it works. So I think it's just not been done really. But yeah, this model is quite new, I would say.
okay.
And I think Pirozzoli's group, they had a decent paper on
something like that.
Yeah, something
It's not
similar.
about semi-implicit.
No, it was
stuff.
yeah.
Good. Thank you.
Yeah, thank you. Great questions.
I mean, if there's another question, actually, like it's 3 p.m. and I mean, of course, like I am Shahab is staying here for the rest of the afternoon. If anybody wants to make some more detailed question, you can. So we can thank again Shahab for your talk.